today I will start with the introduction for the second assignment, and then we will go to actual topics and mainly spend our time with failure mechanisms in passive components. For the literature, quite same as previous. I in fact changed these books into gray because I don't think that it is relevant to really go into the books. You can find all necessary information from the internet. So books, especially in the packaging area, are a little bit, let's say, challenging because the packaging technologies evolve very, very rapidly, which means that especially for the, let's say, high-end, most novel packages, highest integration packages, the books are already, let's say, old when they appear. On the other hand, some of the package structures are basically exactly similar to what they have been during the last 20 years. Okay, then I also put here the standard. It's mainly related to, let's say, when we go to the active components and electron migration, so maybe more relevant for the next lecture. I would like to emphasize that this newest version from the JEDEC standard is not free, but I have uploaded for you an older version. I think it was 22B or something like that in my courses. So basically the content is almost identical. You can look it through if you want. So that's naturally this kind of nice to know information. So definitely not required in that sense. Okay, maybe that's enough from the literature. So basically now we could jump into the second assignment. So hopefully you can now see my Word document. So these are the instructions which is already available also in the My Courses page. So I think this is, let's say, should be, or the intention is that it is a little bit more relaxed assignment. Then also the instructions are also a little bit more flexible. So basically the idea is that, or the objective of the task is just to, let's say, introduce some aspect relating to printed circuit boards or substrates in general for you. So this is not to, let's say, the purpose is not to cover the whole area in detail, just to have you something which maybe is motivating to read this kind of a small part of printed circuit boards. And it also means that you have different topics. So basically there's, in my courses, I will show you in a minute, there's 10 subfolders, and the subfolders are named from 0 to 9. And your personal topic is dependent on your student number. So for example, if your student number is like this, you take the last digit and then you go to the folder number 6, and that gives you your topic. Or if you have, in some cases, you can have a letter at the end, but then always you take the last digit. So this defines your personal topic. So maybe I will immediately jump to the, okay, sorry. My courses, so when you go to the assignment and exams, this should be now the student view, so you should see it exactly the same. So here in the second assignment instructions, there's only this same document, which I've already showed you. So nothing specific here, just this one and then the deadline. But okay, it's a little bit slow. Here are the folders. So for example, if your student number ends with a 0, then you go here and you have a little bit, let's say, more information or instructions inside. So in this case, your topic is solderable surface finishes, and there's one sentence stating that what you should include in your, let's say, submission. And here is also the material which you should use. If we go, for example, to the next one. So number 1. So here the topic is conformal coatings, and your submission should basically answer these 2 questions. What are the most commonly used conformal coatings, and how conformal coatings can improve the reliability in harsh environments? And then there's again some material, and now this, especially this one, is relatively large. So I have highlighted here that you should only concentrate chapters 1 to 3. And then the other material here is just nice to know. You don't need to use it, but if you want, you can quickly check it through and pick something else from there. So this is the idea. So 10 folders, and you pick your own topic based on your student number, and then we have just the standard submission box here. And the deadline is here, 16th of November. So the same day as we have also the lecture on the printed wiring board materials. So let's quickly check what is the actual requirement. So there's 2 options, so-called preferred option, and then a backup option. And I would strongly recommend this preferred option. And then the idea is that based on that material, which is available, you formulate some kind of a graphical or visual presentation. So it could be, for example, you make a poster out of that, you make a mind map or concept map out of that. If it's, let's say, something related to materials and manufacturing processes, then maybe a flow chart on the manufacturing process could be quite nice. It could be just a picture collage containing, let's say, some links to different pictures. So not just that you put in Google Pictures, you put your topic and then you take 10 pictures and put them into one slide. Maybe not like that, but somehow link these together, or whatever kind of visual representation what you let's say can imagine. So I really encourage you to be innovative, creative, and pictorial. So some kind of a nice visual thing. And if you think that you cannot do this one, so you are not that artistic or whatever, then you have the backup option. So you can do it also in the traditional way, just write a short essay on the topic, and then if you write an essay, then it should be about 1 A4 page. 2 pages is absolute maximum. So don't start writing a long report on that topic. Just 1 or 2 pages. Or you can prepare a few PowerPoint slides. And there, if you pick that one, then the definite maximum number of slides is 5. So the point would be that you would be able to show the topic with just one view, like mind map or poster, and that would be all. And sorry, please pay attention that the objective is not to cover all possible things which is related to that topic. So the point is just that you show some key aspects related to this specific subject. And as I said, there's in each of the subfolder there are some short instructions what you should include, what you should show with your presentation on that topic. So here is just the submission instructions, nothing specific there. You just submit one file, and you should have your surname there, and then the file format can be whatever. So whatever in that sense that I can look it through. So consider that I'm using normal Windows workstation. So if your submission can be opened with that one, it's possible to have just a TIF picture or PDF document or JPEG or PowerPoint or whatever. Okay, there's a question in the chat. Should the preferred options be only one page or can they exist? So I would prefer that it's one page, but of course, I have seen during the years several extremely excellent, let's say, interactive versions, something which I don't even know how the students did it. So for example, like that you are running a program, then you click one picture and then something opens there, or link takes you somewhere else or whatever. This is definitely not something which is required. So it's up to you to decide what you want to do. But maybe the point here, I will first go this one. So the point is not that you spend huge amount of time on this. So as you remember from the first lecture, there was 10 hours allocated for this assignment. So basically 1 full day, that should be enough for you. And I know that it already takes few hours to read the material. Sometimes there's let's say a few dozens of pages in that material. So what I kind of consider is that maybe you spend about 50% of the time just going through the material. Of course, you can use some additional material. You can go to Google and just search something, Google Images, or you go to some company home pages or whatever, and then pick something extra from there. And then you spend another, let's say, 5 hours or something like that, just composing your output. And if you use some additional material, then please add the references. So if you only use that material which is provided to you, you don't need to add those as references in your, let's say, mind map or whatever. But if you use some additional material, then please put there the references where you have taken that material. And then maybe the point which is of interest for you most is that how this is graded. So basically the grading criteria is that if you do something, if you just show that, okay, I have read the material and done something, then you get 2 points. So meaning that you have covered the topic and you know something about conformal coatings or solderable surface finishes or whatever. Then you can get also 4 points if you do it with an excellent way. And of course, also here, when this is, let's say, you have so much freedom, it's impossible to define exactly what is excellent and what is not. But here I try to, let's say, point out what is meant by excellent, that with way or another, you show me that you have understood the big picture. So you put some kind of your own contribution to the subject. So for example, you link, let's say, the materials, the manufacturing methods, the performance, and the reliability somehow. So that when someone like me looks your submission, your flowchart, then we know that, okay, because of this specific material, also the manufacturing process must be this one. And that means that the actual product or material or whatever has certain properties, it has certain reliability performance or something like that. So that is the, let's say, the idea there. So you can get these 4 points only if you do your assignment with this preferred option. If you then decide that, okay, I'm not able to do any visual presentation, I will do it in an essay or PowerPoint presentation, then you can either get 2 points. So it's only pass or fail. And in practice, what it means that if you write something on the paper which is relevant, then you anyway get the 2 points. So as I said, the point here is more to get you acquainted with some topic related to printed wiring boards. Not that you will, let's say, all learn the same new things, just maybe to add a little bit of motivation for that area, this substrate, because it is still very, very important from let's say, if we think about modern electronic products, printed wiring board, it let's say, affects drastically on the cost. It affects quite significantly on the performance. It affects on the, let's say, miniaturization options, and it also affects on the reliability. And of course, for the reliability part, we will, let's say, concentrate more on that lecture when we have later, what we have later on. But the point here is just to highlight these different aspects related to printed wiring board. So the other topics there are, for example, flexible and stretchable circuits and these kind of things. These kind of modern things what you could, for example, use in smart clothes or whatever. Okay, so I hope that the instructions are clear enough. I know that they are a little bit vague, but that is also the point, so that you have your own freedom to submit the things which you consider important and the way you think that this is best represented. Okay, any other questions or comments? And of course, again, if you, let's say, end up some questions during the process, then please just email me. I'll try to clarify and explain in more detail that specific topic, for example. Okay, good. So it seems that you are fine with the explanation. Good. Then we can jump back to the actual lecture. So now a question: are you seeing the presenters mode or presentation mode? So
presentation mode.
So it's okay. Good. Thanks. Okay. So a few more generic words on this, let's say, third part of the course. So as I said when we started today, that the idea now would be go and have case examples from different levels. So the idea would be kind of that we start from the inside of an electronic product, so in the component level, then we go to the packaging level, and then we go to let's say board level, so printed wiring board, solderings, and connectors. And all these levels, as was already discussed in the first part of the course, they all have their own specific failure mechanisms, and they have their own acceleration factors. So of course we have, for example, temperature each and every level affecting the reliability, but the mechanisms might be different, and then also the, let's say, the solutions in order to improve the reliability, decrease the failure rate, mitigate some failure mechanisms might be different in different levels. But the idea for all these levels is that we have enough information on the actual functionality. So what these parts need to do. So what is the functional performance requirements in different applications. And then we know the typically used materials as well as the manufacturing processes. So if we know these three things, then we have much more means to, let's say, brainstorm the potential failure mechanisms, why now the smoke came out from the product at this specific application under these specific conditions, and so on. So of course, then we would also have this, let's say, product level or system level, but as this is more, let's say, product or system dependent. Our examples might cover something here, but the focus is on these parts, which definitely, let's say, we have in every electronic product, we have these parts there. So the same thing is kind of also highlighted here. So how do we, let's say, approach this topic in the third part of the course is shown with this. This is from one of the course books, this Tummala's microsystem packaging handbook, and there he also shows that this is, let's say, the manufacturing flow from the component level up to a device. And now we start here in the, let's say, in the actual components, either active components or passive components. And today we will mainly concentrate on the passives, and then on Thursday, the actives. So one more slide, which I already showed you beforehand, or in the first part of the course, is that where these failures are occurring, and now we are basically concentrating on this part. This is the largest fraction of failures, but of course not all failures are related to parts, which now we consider the components in this these lectures. So starting from the passive components, so I just picked up a few images from failed passive components. So tantalum capacitors, electrolytic capacitors, standard resistor, thin film or thick film resistor having some corrosion failure. So in fact, in few minutes, I will go in a little bit more detail of our own case example from this kind of a failure mechanism. This I cannot even remember what this was, maybe also an ceramic capacitor, and here kind of just showing what could be the final outcome of, even we have this kind of a component which cost is something like one cent or 1 penny. That's basically the cost of a failure could be quite severe if we end up having this kind of a outcome. So maybe you remember something with Jonas also showed this burned IGBT module. So it means that the failure in simple low-cost component can also lead into a very severe failure. Okay, so in general, the failure modes in the let's say all electronic components, we can basically categorize the failure modes in three different categories. We have either open circuits, we have short circuits, or then we have changes in the electrical parameters. So it doesn't matter if we are talking about active components or passive components, but of course the failure mechanisms behind these failure modes can be totally different, because they are typically dependent on these three things which are already mentioned: the functionality, the materials used, and the manufacturing methods. And now, of course, in passive components, we have different types of structures depending on if we are talking about thin film resistors or capacitors or varistors or crystals or switches or whatever. So today we will go through few case examples from this and this. So in general, when we are doing failure analysis from any component, passive component, or this basically also is as well applied for or applicable for active components, is that we need to know about the let's say the functionality, the electrical and physical basis of the component. So what is it supposed to do and how? And then we should know the internal structure and how these structures and materials have been manufactured, because always every manufacturing method has its advantages and disadvantages, and for example, to quality, the defects are related, quite often related to manufacturing methods. Maybe in general, one can say that the reliability of passive components are not typically that much emphasized. First of all, they are very cheap, so typical cost is something in the order of cent or few cents. But on the other hand, for example, if you think about one of the largest electronics companies in the world, Murata Electronics, they are making billions of profit, and their main product is ceramic capacitors. So in that sense, also the quantities are extremely large. Quite often, the passive components are quite easy to replace. I mean that if you are able to pinpoint that, okay, this is the component which has failed, it might be quite easy to replace. Why? Because typically passive components have relatively low amount of IOs. So quite often it's just 2 or 3 IOs. And the solder interconnections are typically visible. So yeah, they are not like underneath of the component, like for example in the active components. So it is possible to let's say replace the failed component. On the other hand, when we are talking about a component which price is extremely low, it also means that the manufacturing process must be really high volume. So typically high volume processes are also very well controlled, and that could indicate that the quality of those components is quite high. So because you can manufacture them in millions, and you can also test and inspect them with automatized ways. So that means that typically the components are quite reliable. But then, of course, the challenge is one part of the challenge is coming from the, let's say, higher integration and miniaturization. So miniaturization could only be that the size of the component is going smaller and smaller. I will have a few words on that in a minute. And then also let's say the integration in that sense that some of the passives are integrated together with more let's say challenging and costly components like multi-chip modules, system in packages, and these kind of things, which I'm sure Glenn has discussed quite much in the MMI course. I have few let's say examples coming in a minute. So we need to think that we have passives and actives in our product, and we need to maybe have slightly different viewpoint, but it's not only that the passives are cheap and easy to replace. Sometimes they can be really difficult to let's say replace because they are integrated in highly integrated, very costly packages. So at least for those of you who are now also taking the Mervis course, Sustainable Electronics, you are more than well familiar with this one. So this is a picture from Galaxy Watch. And here we have the, let's say, the main active components, 7 of those. And here I have a cross section from this, let's say, system on chip, the main brains of the watch. And if we look inside, so we see that there's the actual application processor, so the, let's say, the logic part. Then we have several memory dies, at least 2, which are stacked. Most probably you cannot see them, but here and here there's 2 stacked memory dies. But then in addition to that, there might be some integrated passive. So quite often when we are talking about processor, then you have these decoupling capacitors, which from electrical point of view should be as close as possible with the processor die. So even if you remove the processor from your desktop computer and you have this, for example, Intel's processor, and you look underneath, you see that in addition to that actual processor chip, you see there are few capacitors which are needed there. So also here, cannot remember now exactly, but I think also here we had at least one capacitor which was integrated in very close proximity of the actual processor chip or die. And of course, in this product, we have also some other actives, let's say smaller components, typically land grid arrays or wafer level chip scale packages. So in total, we have there something like maybe 30 actives in this smartwatch. And then on top of that, as we can see in between the actives, there's huge amount of passives, something like 500. It's of course quite tedious work to get the exact number. So for this again for the sustainable electronics course, I tried to let's say study and count all the different sizes of passive components there. So not only resistors and capacitors and inductors, but also some other like connectors, this microphone and so on. And as you can see from here, there are different sizes. And maybe from here, better to see that some of the passive components are extremely small. So currently in these kind of a modern handheld consumer electronic products, the smallest chip resistors and capacitors, so the size is so-called 00501, which means that the dimensions are such that the length or width of the length and width of the component is 250 micrometers times 125 micrometers. So basically 1/4 of a millimeter times 1/8 of a millimeter. So basically, at least with my old eyes, I really cannot anymore see without any microscope the smallest components there. So you can also think that if you would need to replace, for example, this specific component here, where the size is fraction of millimeter, you need to desolder it, and then you need to apply the new solder material and then apply a new component and solder it back. So with let's say manual tools, it would be impossible without destroying the adjacent component. So for example, with soldering iron, it's not possible. Of course, with this let's say automatic robots, it could be possible, and maybe even let's say financially feasible, because the cost of that component is very small, so you don't need to scrap the whole watch if some of the passives would have failed. Sorry. So this was just an example of let's say the huge number of passives and different size of passives. And here I have another example, and this is from Samsung Galaxy S8 phone, which was our reverse engineering topic, let's say 3 years ago, and maybe also some of the components we will study also this year in MMI course. But this is now from the Wi-Fi module. So it is highlighted here. So this is the motherboard of the S8 phone, and here at this corner you have the Murata's Wi-Fi module. And just if you look at it like this, it looks quite simple. Okay, just one computer component there providing the Wi-Fi connection. But then if you start looking through it, so here we have a trans illumination, let's say X-ray image from that specific component. So what we can see is that in fact it contains huge number of components inside. So it's not one single component, but it's a multi-chip module or system in package component. So we can see that there are several passive components like this, and then there are some actives because we can see wire bonds here and here, and also these small solder spheres, which we can see here, these black dots, they also indicate that somewhere here we have also some larger silicon chips. So unfortunately, when we are using trans-illumination X-ray, the silicon itself is completely transparent, so we cannot see the actual chips. Maybe a little bit better view is when we are looking the same component from the side or a little bit angle, so you can see really the complexity of that one specific component. So huge amount of capacitors and resistors, and then most probably here we have a larger silicon die, and then at least here, here, and here we have some additional silicon dies. So it means that within that one package, there's already several dozens of active and passive components, meaning that, of course, in these kind of, let's say, packages, this term known good die is extremely important, which means that when you are manufacturing this kind of a component having or package having several components, you need to be sure that all the individual components which you put inside that package should be functional. Because after you have overmolded this manufactured this package, then it's practically impossible to replace anything. So it means that all the components really must be tested and screened so that they don't have any hidden defects, latent defects, or these kind of things. Okay, so this was my point here, was just to try to motivate that even passive components might be simple and cheap. They also might be quite challenging from the reliability point of view, and also the failure costs can be, let's say, not at all dependent on the actual component cost, because they have these indirect effects. Okay, so then maybe jump to here. So this is again just a kind of an example for you. I don't mean that you should try to remember everything here, just a big picture. So in the, let's say, different columns, here are resistors, different types of resistors. And maybe what we are missing, this is a little bit, not even a little bit, quite old table. So what we are missing here is the thin film type resistors, which are maybe most common or second most common in modern products. So of course we have these, for example, in the Galaxy Watch, most of the resistors are this kind of a thick film type, one could assume. Then of course with some other applications where one needs higher currents, higher voltages, higher powers, and the space is not that limited, you need to have larger variety of, for example, resistivity values, then you can have different types of resistors still. And here is just in the rows, there are these, let's say, typical failure modes, opens, shorts, and parametric shifts. And then I have tried to highlight the, let's say, the mechanism behind these different types of failure modes with different colors. So if there is a red dashed rectangle on that type, then it's something related to moisture and possibly some impurities. So one could say that that's an electrochemical failure. If it's green dashed rectangle, then it's an electrical failure. And then if it's a, let's say, blue rectangle, then there is something mechanical or thermomechanical related to that failure. So here again, we see that the same failure mechanisms, which we have been talking through the whole course, they are also valid here. And basically, every different type of resistor also have these typical failure mechanisms, which are either driven by chemical things, mechanical things, or electrical things. And then I mark here, just wanted to highlight one more thing. This is mechanism which, let's say, one cannot directly put any of these categories. It's so-called silver leaching, and silver leaching to solder, and that is maybe more metallurgical problem or manufacturing quality problem. And I will, let's say, explain this one with the next slide. So here we have a, let's say, typical structure of an thick film resistor. So maybe if we start from here, so in thick film resistor, most of the volume is just substrate, doing nothing. So this part here, we have an aluminium oxide block. So just ceramic block, which is our, let's say, building block for the actual substrate. And then on top of that, the actual resistive layer has been manufactured. And now this could be either thin film, so something like evaporation or sputtering, or it could be thick film like screen printing method. And in fact, you can see here this small groove maybe, and that is not a defect. It is because of laser trimming. So in fact, even the cost of this component could be something like 2 cents, 1 cent, 3 cents, something like that, depending, of course, how many you are purchasing. Even or still, every component has been trimmed. So what is actually happening in the trimming is that the in situ, the system is measuring the resistance value. So first you have a, let's say, lower resistance, and then you start burning with the laser the resistive material off. So you decrease the cross section of that material, so increase the resistance or resistance, and then when you have achieved the target value, then you just stop it. So basically, I hope you understood. So I think this is quite obvious, but if we look from the top, I don't know why my mouse is doing like that. So from the top, basically you are measuring the resistance, and then with the laser, you just start burning here material off. So you decrease this cross section, so you increase the resistance, and that's how you trim it. And this you can see here. Okay, let's go back to laser pointer. And typically, then let's say after the trimming, the actual resistive layer is protected with something, and quite often it's a glass material if we are talking about thick film or thin film resistor. So some kind of a glass. It could be lead glass. Still, even lead is prohibited, but still in some cases you can use it, or it can be some other glass, for example. And then there could be an additional layer, for example, silicone, which we are seeing in a minute. Maybe the more important thing is the terminal, so how you make the electrical contact. So now you have here at the surface, you have the let's say the resistive material, but you need to somehow electrically contact it. So how do you make it? So typically you have this silver paste there. So that's silver flakes together with either let's say glass particles or organic binding agents, which is, let's say, applied at the ends of the components, so that makes the electrical contact from the resistive material to this end termination. But as you cannot solder this kind of a silver directly, typically you apply there some diffusion barrier, which is nickel, and then you might have the solder coating, because you cannot have nickel there without some protective coating. So it could be gold, but typically in these kind of components, gold is too expensive, so you just apply solder there. So some kind of a solder plating. And now this, in the previous slide, this silver leaching means that if this nickel layer here is too thin or not uniform, then basically the silver can dissolve into the liquid solder during the soldering operation. And that, of course, is quite bad from the reliability point of view. First of all, silver is making the solder harder, so less ductile, and also silver has this tendency of migration. So it's also very reactive, especially if there's a, let's say, sulfur containing impurities in the ambient. And this is in fact what we are looking next. So the first case example which I have here is a surface mount technology resistor case. So this is a few years back, one of the, let's say, not that large Finnish companies contacted us and said that, okay, we have some problems with our products. Basically these were in medical technology area, and these products were used in hospitals. And the problem was that the boards, or these control boards, they started to fail roughly about 1 year after taking into use. So these are kind of in the application where the usage is quite continuous, but still the lifetime of about 1 year was definitely too small. So the lifetime target was something like 10 years, and they start seeing failures already after 1 year. And then they had, let's say, pinpointed the problem that these resistors which are shown here, the resistance value for those had increased drastically. So basically, even some of the components were open circuits. And then they provided the components to us and asked that could we look into this, let's say, topic and consider what could be the reason behind. And here we have, let's say, 3 identical resistors side by side, and they are now called here R8, R9, and R10. And they stated to us that, okay, this resistor number 9, this had failed, and these are still working without any problems. And the reason why these look a little bit ugly is that as this should have been this kind of a high reliability product, the whole component board, so the substrate and the components after the soldering, they were covered with this conformal coating. So basically everything was covered with silicone layer. And now in order for them to make the, let's say, the electrical measurements, so to really measure what is the actual resistance, they had to, let's say, penetrate through the silicone. So that's the reason that you can see these silicone residues here. But this is just to measure from here to here the resistance, from here to here and here to here. And then we considered that, okay, we need to start studying the internal structure. And maybe the first guess always is that there's something wrong with the solder interconnections. So either cold soldering, so not proper solder formation, or very large voids which are also typical for these kind of components. And that's the reason that first we made some trans illumination X-ray just to check, do we see a huge amount of voids? And the answer is no. We see a small amount of voids, and they are all, let's say, underneath the component, but only very small amount. So definitely this amount of voids, so these wider spheres here, they cannot cause electrical problems or even mechanical. Let's say that the solder interconnection would be mechanically too weak. So then we wanted to see that how the solder joints look inside and make cross section. So here now I have indicated with red dashed line where the cross section is made. So now we are looking, let's say, from this direction. So we can see that in fact the solder interconnections here and here, they are of, let's say, very, very high quality. So no defects, no cracks, very nice wetting, no voids, and everything is, let's say, excellent. So we can kind of already exclude that the solder interconnections would somehow be responsible for the problem. But we know that the resistivity from here to here was too high. Then we started to concentrate on the actual resistor area, so the top surface of this component. So when you are looking a little bit closer this part, you see that here we have the silver metallization, this one, the nickel, the tin, and this is our resistive material here. And in fact, here we have the glass protection, and this is the silicone conformal coating. And all these materials were just confirmed with this EDS element map. So basically here is a map which is showing different materials with different colors. So we know that, or see that, okay, here, for example, we have the aluminum oxide substrate, which is here. Here we have the silicone coating, which of course is mainly composed of silicon. We have here the silver, which should be the, let's say, contact metallization. We have the nickel as a diffusion barrier, and we have the tin, which is the solderability coating here. Already from here, we can see that, okay, this part looks a little bit strange. The silver is not continuous. So if we think that we should have the, let's say, electrical contact from here to here, and then from here to here to the component, then this looks a little bit suspicious. And then when we took a little bit more analysis on that part, and now here in this part where the silver was not continuous, I have here 2-point analysis, 0.6 and 0.12. So 6 and 12 here. What we identify here is that we should have silver. We have silver, but also we have very high amount of sulfur. So almost as much sulfur as with silver, or maybe half. But still the sulfur content is that high that it is clear that there is sulfur. And then we checked the other materials in the component, where the sulfur could be coming from. And we checked the glass, we checked the aluminum oxide, we checked the silicone, and we couldn't find any sulfur source. So it means that most probably it is coming from the use ambient. And then what we also could notice that here with highlighted with these red arrows, there's a kind of a delamination or crack between the silicone conformal coating and the glass passivation. So the adhesion was not that good, which means that here we have, let's say, a direct path for example, moisture to penetrate inside the component, inside this critical area. Then we studied this issue a little bit more, And we, for example, took this kind of element maps also from the top surface of the component. So if we check this part here, we can see that we have there the silicon, we have there the tin, we have there a little bit of nickel underneath the tin, but just at this point here, where we should have the, let's say, the electrical connection from the solder interconnection to the resistive material which is underneath here, we also have silver and sulfur, meaning that for some reason this sulfur has been able to penetrate here at the contact metallization and reacted with silver, forming silver sulfide and kind of corroding this electrical contact. So in order to conclude, we noticed that sulfur was present in all those failed resistors. It was also, sulfur was also found in the non-failed or functional components, but not that much with the failed ones. And always when we detected sulfur, we also detected silver there. So it's quite clear that the actual mechanism was reaction between silver and sulfur and formation of silver sulfide. We also noticed that there's a, let's say, poor adhesion between the glass passivation and silicone conformal coating, which means that there's a direct path for moisture and sulfur to penetrate. And then we also looked a little bit about the literature, and we found out that sulfur has very high solubility in silicone. So basically what it means is that if you have some sulfur in the air, like in the form of hydrogen sulfide, then silicone kind of absorbs that sulfur, and the concentration inside the silicon can be, for example, even 100,000 times higher than in the surrounding atmosphere. So if you have there, let's say, parts per million concentration of hydrogen sulfide, then you might have even few percent sulfur in the actual silicone. So it means that there's a driving force for reactions, and now the only question was that where this sulfur or hydrogen sulfide is coming from, because of course we were talking about an equipment which is used inside hospitals, so it's not in a pulp and paper factory, or it's not in the petrochemical factory, or it's not a wastewater plant or something like that where hydrogen sulfide could be there. And let's say the only reason which we figured out could be that because they wanted to be have extremely reliable product, then the actual electronics were put inside this kind of a, let's say, enclosure. So this one is stainless steel, and the electronics was somewhere in here. And okay, this looks ugly, but maybe I'll test another color. Look, so in order to, let's say, protect the electronics, even they had the conformal coating basically covering the whole board like this, they used rubber sealing here. So this kind of an O-ring type of sealing. So basically there was some mechanical bolts through here to tighten the lid to the stainless steel cover, and a rubber sealing, maybe sealing ring or whatever you can call it here. And we all know that when you are, let's say, vulcanizing rubber, you need sulfur in order to do that. So the only reasonable explanation what we find out where the sulfur could come from was from these sailing rigs. So in fact, by trying to be really reliable and hermetic, in fact, they kind of initiated the actual problem. Of course, this is not a, let's say, 100% sure that this conclusion was correct. So we are quite sure that these conclusions are correct, but the origin of the sulfur, of course, could be either here, or then it could be just that the let's say the ceiling was for some reason leaking, so the sulfur was coming from either sulfur or hydrogen sulfide, or some chemical impurity containing sulfur was coming from the used environment. Okay, so hopefully this was of interest and informative for you, so that the point was to show that even we have a component which should be of high quality, even all the sensible tricks for improving or verifying the reliability, like conformal coatings and these kind of things were done. The soldering quality was excellent and so on. Even that case, sometimes one can enter reliability problems which might have very high financial stakes or financial consequences. Because you can, of course, imagine that if you are selling something, a product in the field of medical engineering, it is going to the other side of the world, and you, let's say, your assumption is that the lifetime is 10 years, and then you start seeing failures after 1 year. That's from a business point of view, that's a really, really difficult situation. So that was the, let's say, the point for this exercise or this case example. Then I have 2 more examples. I just need to check what is the time. Okay, so we have about 20 minutes time left. So for the, let's say, capacitors, basically the idea is the same. We have several different types of capacitors, which of course mean that they have different materials inside. They have different manufacturing methods. Like, for example, electrolytic capacitors. Maybe all of you, if you have been, let's say, playing with electronics, know that sooner or later all electrolytic capacitors will fail because they will dry out. They have liquid electrolyte inside, and if you use them for 15, 20 years, they will dry out, and then you lose the functionality. So in that sense, that's a clear wear out failure mechanism, but also kind of an expected one. And for example, temperature is critical there. So if you use them in high temperatures, high operational temperatures, of course, then the drying of the electrolyte happens faster, and then your lifetime will be cut. So also the, let's say, the design for reliability on that kind of a failure mechanism is quite simple. So you can predict the lifetime quite well, and you can predict the lifetime as a function of temperature quite well. So increasing the lifetime, you just need to decrease the operational temperatures, either with passive cooling or active cooling mechanisms, or better thermal design or something like that. So just an example that these kind of a failure mechanisms from design for reliability point of view are relatively simple. But then we have other types of okay, there's a question in the chat. For the capacitor, is it so that some types need a recharge or applied power to maintain when stored, and why? Okay, so I'm not that big expert on the capacitors. Of course, the let's say electrical energy which is stored is typically discharging slowly, and it is dependent on the component itself, but it also dependent on the other circuitry. So to which you are connecting the capacitor, and I would say that all capacitors, they are losing their energy sooner or later, and it's dependent on the actual component as well as the circuitry to where it's connected. So, but the difference is, for example, between different types of capacitors. Unfortunately, I'm not the correct person to answer. Maybe in the, for example, in that Harper's passive component handbook, which was the first book in the first slide showing the reference literature, I would assume that for example, contains this kind of an information if you are interested. So, for example, now of course there's quite a lot of discussion on the supercapacitors to be used as an energy storage, sometimes to, for example, replace batteries and so on. So it's a, let's say, compromise between the energy density, the efficiency, and then also the, let's say, the lifetime. Sorry about not being very let's say, accurate on the answer. Okay, so another case example, and this is also coming from quite close. So maybe not going to mention the company, but if you Google, for example, Finnish companies who have published something on reliability of ceramic capacitors, you will find one company which is located in Pitäjänmäki, and same company which have had quest lectures already this course. So maybe not more than that, but they have, for example, have had this kind of a, let's say, case on chipping or corner cracking of ceramic capacitors. So this is maybe not the best visualization, but maybe you can see with these red arrows I have pointed this kind of a corner cracks here. So maybe again I try to draw something, but the point is that when we have large printed wiring board, and then we have these ceramic capacitors, the small ones here, we solder them on the motherboard or printed wiring board. You cannot, like in that previous resistor, the solder interconnection, if I, if I draw, so this now with the red color, I draw the solder interconnection which we saw in the resistor in the previous case example. So basically the idea there was to have as large volume of solder as possible. But in the ceramic capacitors, these are mechanically quite, let's say, fragile. So then there's design rules that how large the solder interconnections would be. So typically, maybe I will use light blue. The solder interconnections with the ceramic capacitors are something like this. So as you can see from these images, this is the copper pad. So the solder, this one, it's not going up here. It's just quite small amount of solder here. And same with this one. Why is that? Is that we want that if something is bending or twisting, that, okay, what color? Maybe black. So if we are applying a force here, so this board is bending like that. Of course, with huge exaggeration. So this component will be bended, and we will end up seeing cracks like this. And these are called corner cracks. Why? Because typically, if you look from the top, where do I draw it? Now we are looking the capacitor from the top, then the corner cracks, they are like this. So they are not penetrating always through the component like this, and they are only in this lower corner. And now, of course, that is problematic with the electrical performance point of view. Sometimes they can be so close to the corner that they don't even touch these electrodes. So here you can in fact see the electrodes. And this gray material is the dielectric, the barium titanate, which is in between the capacitor plates in the capacitor. So now when you have this kind of a corner crack, then you only cut small fraction out of the, let's say, capacitor plates. Not all, but small fraction, which means that it might be that your capacitance value is just decreased with a certain amount. So the electrical functionality will be changed. It's not a permanent, in that sense, complete failure. It's just that the capacitor is not functioning as it should be anymore. And this, of course, quite often means that your circuitry just starts to behave strangely. It's not failing completely, which would kind of be easier to analyze, but you end up having these kind of things. And in fact, why this was observed, these cracks came during testing. So when they, let's say, manufactured these printed circuit cards, then they wanted to be sure that they are reliable. They pushed the cards in the bed of nails, and in that process, these nails, if one of the nails is a little bit higher than the others, it causes small local bendings. And that caused these corner cracks in these capacitors. And that was, of course, very annoying problem because you may not detect it immediately with the electrical testing. It is not mechanically fracturing because you can see that this, for example, this laser pointer back. So this solder joint here, there's no defect here. So mechanically, this component is perfect. Electrically, it might be quite close to okay, but still there's some problem with the actual capacitance value. In fact, I put this link. This is not in your slides, but I added this link into the My Courses page. So if somebody is interested in this kind of failure mechanism, please go to this TDK homepage. They have quite nice solution guide for this kind of a corner cracking of the capacitors. One option where you can, let's say, decrease the probability of this kind of a failure is use, instead of so-called normal capacitor, you use flex capacitor. So both of these components, they are coming from Murata again, but this has a flex structure. So here, this contact metallization here is rigid. It's copper and glass. So it's basically a thick film, rigid contact metallization. But this contact metallization here has only very thin copper layer, but on top of that there is this silver layer, and now that is not made with thick film, it is organic. So it's basically a conductive silver glue. It's a silver flakes and epoxy matrix. On top of there is the nickel plating. Maybe you can see the dark gray here. So you still need the diffusion barrier. So otherwise, this is exactly the same structure what we have seen previously, but now in this case there is a layer which is more flexible than the other structure. So now if there's some bending of the motherboard, then some of the energy is absorbed by this flexible organic or composite material containing metal and organic material. So this increases the durability of this kind of a capacitor in conditions under stresses, bending stresses. Bending, of course, could be coming from the handling, but it of course could also be coming from the thermomechanical effect. So depending again on the actual structure of the component. Okay, so this was just a very simple case example in that sense that I couldn't provide more information on this problem, but the point was to highlight really the effect of the actual structure of the component on this kind of a failure. And as I said, if you are interested or ever face this kind of a problem, go, for example, here, there's quite nice data available there. Then another, or the final case example for today. So we have 10 minutes time. So let's finalize with this one. So this is a case for varistors. So basically, voltage dependent resistor. So you are better familiar than I am about this, the functionality of this kind of a protected circuits. But basically the idea of a varistor is to protect your circuit from over voltages. So if you have here the power supply, and if there's a, let's say, moderate or acceptable voltage over this varistor, then only very minor current is leaking through it. So then you have your circuit with the correct voltage there. But if for some reason, like power cut, lightning, or something like that, you have a voltage peak, then when the voltage is increased, then this kind of a breakdown region, after the breakdown region, then the current jumps up. So basically, if the voltage is high, then the current goes through the varistor and protects this circuit. So this is basically the electrical functionality of the component, and in fact, the structure is almost identical to the ceramic capacitors. The only difference is let's say, the insulating or the dielectric material. So in ceramic capacitors, this is typically barium titanate because of the electrical properties, but in varistors, that's a combination of different types of oxides. So mainly zinc oxide, but it also can have some other oxides like bismuth, cobalt, and manganese oxides inside. And now let's say the case behind here was that this one Finnish company, telecom company, and not the big one, a smaller one which is not existing anymore. They let's say manufactured motherboard or printed circuit component boards for telecom applications, and the point was that they had used certain type of varistors in order to protect the circuitry. So basically, this varistor was very close to the power inlet. So basically, if I remember correctly, it was just standard 240 volts, which was kind of put inside that board. And then they were having some problems. Their customer, in fact, the big N, had some problems in the field that these, let's say, these boards burned. And in fact, also then they provided these boards also in some research organization in Finland, and even one of their labs almost burned because of this problem. So then they went back, okay, what kind of changes were made and so on. And then they noticed, okay, their sourcing, let's say, department has changed the component, this varistor component, so that instead of using components from manufacturer E, maybe I can say it here because it's the good one, it's the EPCOS component. So this is, let's say, high quality, high cost varistor. And then they have changed the component to a cheaper one, which is in here marked as S. So I'm not going to mention this company name because this was the, let's say, the poorer quality company. And they noticed that, okay, after the change from this EPCOS to low cost S, then they started to seeing these kind of problems. And in fact, they consider that it might be that when the guy who is installing this board into the base station, he needs to use a little bit of force when plugging in the power supply, and that causes small local bending, and that could be the primary reason. So first they asked us to study is there some, let's say, difference in the structure of these components and what could be the reason behind. So first we made, again, cross sections from both components, so from S and from E, so the high quality and, let's say, moderate quality. And we could already see that there's, let's say, significant differences in the contact area. So both had this zinc oxide insulating material, both had silver plates here as let's say, electrodes. Maybe the quality difference you can already see here. So in the E component, the silver electrodes were thicker and more uniform, and with the S, the uniformity was a little bit, let's say, worse. In fact, that was not the primary reason. There's also two additional differences. First is that this S component had thinner silver layer, as you can see from here. And also there's a, let's say, thicker layer here than here, which contained silicone. So I'm calling it here only silicon-rich layer. So basically, it's a layer which increases the adhesion between this, let's say, ceramic material and the silver. So you need to apply here something which improves the adhesion. And here it's thicker, here it's thinner. So these kind of things were differing between these components. And then we did just very simple mechanical testing. So this is our mechanical test. So we had a simple printed wiring board. The components were soldered underneath, so they are somewhere. Okay, again, pen. So the component is somewhere there. We cannot see it. Maybe here you can see it like that. And then we measured how much deflection we need in order to, let's say, break the component. And the typical value, so how much this board was bending downwards for S was 5 millimeters, and for this A, it was 17 millimeters. So clearly one can say that this E component withstands much higher bendings. So it's mechanically much more rigid. These are the actual results. And what we can see that with the E, of course, the scatter was quite much larger, but for the S component, most of or all the components failed with relatively small force. With this kind of a 3-point bending, the problem is that the results are really critical on how accurately you can position this tool, because let's say the stress distribution is extremely, let's say, sensitive to that one. Okay, but anyway, the main point was that when we afterwards detected the failure mechanism, we see that for the S components, all the failures, they nicely follow this, let's say, the shape of the component itself. Maybe that was really bad color. You can't see anything. So the failure is here, like this. On the other hand, with the E component, so with the EPCOS component, it was not the interface which was failing, but the actual failure went through the ceramic material. So one can, let's say that this is an adhesion failure and this is a cohesion failure. So here the strength is based on the actual material property of this zinc oxide, and here the strength is based on the adhesion between the zinc oxide and the silver layer. And then when we studied the fracture surfaces, so this is the fracture surface from the component side and from the solder side. So basically, if we are, sorry, again, I will change the color. So if we are looking what was left at this interface and what was left at this interface, we see that both sides, from component side as well as solder side, we see that there's lots of silicon here and here. So now we can finalize this lecture by going back to here. So if you find a failure where both, let's say, fracture surfaces contain silicon, the only option is that a fracture goes somewhere here, like that. And instead, in this, where we have much thinner silicon-rich layer, the failure went somewhere here inside the bug. So this kind of concludes that here the basic problem was inside the component because of the manufacturing, and by saving few cents or maybe even euros with one specific component, they caused a huge loss with the, let's say, burning boards. Okay, good. That was all, and on Thursday we will continue with the active component failure. So this was all with the passive components.